Hello. In this video, we are going to talk about a new branch of hardware security that exploits high-level synthesis for malicious Trojan attack. And the title of the paper is MHLS, which stands for Malevolent High-Level Synthesis Framework for Watermarked Hardware IPs. This work was published in IEEE Embedded Systems Letter in December 2024. So let's firstly try to understand what is high-level synthesis in the context of design of integrated circuits. So HLS is an automated design process that is used for converting an algorithmic description of an application into its register transfer level counterpart. During the process of HLS, there are several steps that includes scheduling, register allocation, functional unit allocation, binding, interconnect design stage, data part design, controller design, and so on. All these stages are equally responsible for converting an application from the algorithmic level into its RTM. From an attacker's perspective, an attacker can try to insert covert Trojans into the HLS design framework in order to have certain malicious payload. Formally, a hardware Trojan is a malicious logic that is inserted into an IP design during its design or manufacturing process. So far in the literature, most of the works have focused on inserting hardware Trojan during RTL or lower level synthesis steps like gate level or layout level. There are very limited works available in the literature that actually focuses on inserting hardware Trojans during higher abstraction levels or higher abstraction design phases like high level synthesis. In this work, we have leveraged HLS maliciously to insert hardware Trojans. The hardware Trojans are designed in such a way that it remains to be undetected until it's triggered under very specific relevant conditions. And despite triggering, it may not always be detectable. So the goal of this paper or this work is to highlight how a malicious HLS framework is capable of inserting hardware Trojans during the MUX-based interconnect design stage of watermark IP design. So as I mentioned, that MUX-based interconnect design stage is one of the most important stages of an HLS process because it decides what is going to be the switching size and switching capacity of your IP. So while an IP design is being designed, using HLS, MUX-based interconnect design stage plays a very vital role. And that is also equally applicable for watermarked IPs. Watermarked IPs means IPs that contain embedded hidden watermark signature as part of the design flow. Through this presentation, I'm going to talk about how the HLS framework can be maliciously exploited for inserting hardware Trojans. The impact of the malicious HLS framework that is being considered in this particular work is performance degradation or denial of service. Either of the two is possible. There are some approaches of HLS based watermarking in the literature like 1, 2 and 3, which you'll find out when you go to the reference section of the paper, which have all exploited HLS to embed secret watermark for an IP. And most of them has exploited register allocation phase of HLS framework for embedding the secret security constraints, which means that the multiplexer based interconnect design stage gets altered after embedding of the watermark information. And when I say it gets altered, it basically means that the size of the interconnect design stage of the registers, corresponding to the register allocation phase, they get slightly changed because of accommodation of different storage variables. It has been seen and observed that while this process is being done, post embedding a watermark, the MUX interconnect design information of the registers may yield a free port, okay, or a vacant port corresponding to the multiplexer, which can be secretly exploited by an attacker to insert hardware trojans. For example, if you see the scheduling graph, okay, of MESA benchmark on the left side, which is the one without the watermark, and the one on the right side, it contains the same scheduling graph of MESA with the embedded watermark, and you can notice the difference in the register allocations, okay, due to the storage variables. Okay. So this difference in the register allocations are as a result of the embedded watermark due to the swapping or alteration of the storage variables. So the one on the right side reflects the scheduling graph with watermark, and on the left side it reflects the scheduling graph without watermark. If you try to extract the multiplexer interconnect design information from both of these scheduling graphs, it would somehow look like this. Okay, this is corresponding to register B. You will see that the MUX-based interconnect design without the watermark contains 2 pins, while one with the watermark corresponding to register B contains 4 pins, because it's a 4:1 MUX. However, the last port is unutilized or free. Okay, and this is all just because of the change in the register sharing corresponding to the storage variables. So if you go and have a look at the scheduling graph, you will see that register B has been now comprising of 4 different informations. Of course, the last one is not utilized, so rather 3 information, and the one before the watermark that comprises of 2 storage variables that is being stored inside or assigned inside register B. So post watermarking, you see that there is an extra port which is unutilized, which is marked in orange color here. So the malevolent high-level sensors framework accepts the CDFG of the application, which stands for Control Data Flow Graph, the resource configuration, and the IP vendor signature. It accepts a library of different components and the RTL design. It is fed into the scheduling graph, and once the the scheduling graph with the allocation and binding information is obtained, okay, it can be used for embedding the secret watermark signature, from where we can extract the MUX-based interconnect design phase, where the performance degradation hardware trojan and DOS, denial of service hardware trojan, can be secretly inserted. That results into the trojan inserted data path, and that is finally the RTL design with the trojan, which the actual IP vendor may not be aware of. So what is performance degradation hardware trojan? Performance degradation hardware trojan is basically a kind of trojan that enables your circuit to perform the correct functionality and produce the correct output, but with a certain lag or delay. So there is a degradation in the performance, and that therefore it becomes very hard to detect because there is no functional difference as a result of the trojan. The second class of the proposed trojan that we have discussed in the paper, that is embedded or inserted inside the HLS framework, is called denial of service hardware trojan. It is basically a class of trojan that produces open circuit condition or high impedance state as a result of the trojan when it is triggered. So these two refer to the 2 different classes of hardware trojans that are inserted during the MUX interconnect design stage of HLS process. The one on the left side is the PDHD, and one on the right side is DOS HD. And you can see the one here which contains this comparator and the 2:1 MUXes. This is the triggering part, triggering logic of the trojan, and the one that you see here in terms of inverters, this is the one that is a payload. So as a result of this inverter chain, the 4th unutilized port is being exploited by the attacker to produce a delayed output, okay, corresponding to this input register I. while this comparator, it produces a trigger when the value of preloaded constant C becomes equals to this value of I, which is coming from a internal output. Okay? And correspondingly, these two multiplexers are responsible for choosing, okay, this corresponding select line 1 1, okay, when the value of 0 0 is applied. So as a result of which, the output from here produces the delayed version of this input when the Trojan is triggered. In case of DOS HT, what happens is the triggering part remains the same, but the payload part becomes different. Here, what happens is these two TSB blocks, they produce high impedance state when the input of when the control pin of this and this two TSBs, they are triggered at the same time, because it tries to pass a 0 here and tries to pass a 1 here. As a result, it produces Z condition high impedance state, and that results into a denial of service. So this is a functional table or behavioral table corresponding to the two different classes of Trojan. The Trojan gets triggered at I equals to C, and obviously it produces a delayed output, as I said, corresponding to register I. While the Trojan remains inactive, it produces a normal output. In case of the DOS, what typically happens is, it produces high impedance state Z when the Trojan is active or triggered, I equals to C, while in the other conditions, this produces a normal output. Let's do a slight comparison of the existing work with the proposed, okay, Trojan inserted malevolent HLS. So in 2019, the work in 7, okay, they have used malicious HLS tools that can alter the IPs. However, 7 shows the insertion of Trojans only in non-watermarked HLS generated IPs. So 7 did not talk of how to exploit a watermark hardware IP using HLS. Okay, or what kind of vulnerability does a hardware IP expose during the HLS design process. In 2017, authors have proposed functional Trojans in micro 3P IPs of the HLS tool library. However, 4 does not present performance degradation based Trojan and denial of service Trojan. In 2022, authors, this is sort of a detection technique for the Trojan that is proposed in approach 7. So it has assured the availability of Trojan infected RTL code using Bamboo tool for launching functional equivalence checking. However, Bamboo tool does not provide Trojan infected RTL codes for watermarked IP designs like the ones which have been used in this particular proposed work or in this paper. So therefore, it is not capable of detecting DOS HT attack like in the proposed approach as well as the PDST. The experimental evaluation is based on two factors. The first is what kind of overhead does the proposed Trojan insertion achieve. The overhead should be as minimal as possible. So when we have tested it for watermark method, we found out that the overhead percentage is 2.66 and 2.64 for the two different classes of Trojan compared to the baseline IP. This number refers to the gate count of the IP design, and with the increase in number of inverters, okay, it's the inverter chain length. So when we have 10 inverters, 16, 20 and 24, the overhead increases marginally while the performance degradation increases substantially, which is desirable from an attacker's perspective. The attacker would like to have a higher performance degradation at minimal growth of area overhead. This is the power overhead, okay, due to the insertion of the proposed HLS aided hardware Trojans in watermark Mesa. As you can see, the power overhead is also not too high. It's pretty reasonable at around 3% when compared to the baseline. So this table 6 here refers to the area comparison of the proposed malevolent HLS with approach number 7, which is black hat HLS. You can see that the proposed malevolent HLS attains a maximum area overhead up to 2.6% compared to the one in 7, which is 4%. So area overhead of 7 is much higher for similar kind of hardware Trojan like performance degradation. And in terms of the performance degradation achieved, the proposed malevolent HLS achieves significantly higher performance degradation for watermark Mesa compared to 7, which does not have any test cases or instances of testing on watermark Mesa because they did not apply their Trojan insertion for watermark Mesa IPs. These are the set of references which have been used. So approach 7 is the one which we have been comparing with. This was published in IEEE Transactions on VLSI in 2019, and we have also compared with 4, which was published in 2017 in IEEE Transactions on CAD of IC. And these are some of the other important references which a reader could refer to for understanding more about hardware Trojans during HLS. Thank you so much.